So, in the previous video, we have seen the fiber fabrication techniques. Now, in this video, we will discuss each technique one by one. So, as we see here, there are several techniques employed in the fabrication of optical fiber. The most widely used method include outside vapor phase oxidation, vapor phase axial deposition, modified chemical vapor deposition, and plasma activated chemical vapor deposition. Now let us see outside vapor phase oxidation technique. So this method uses flame hydrolysis to deposit the required glass composition onto rotating mandrel. A mandrel is a alumina rod that keeps on rotating, so it is called as mandrel. So on that rotating aluminum rod, what is done? Vapors of the chemical vapors are deposited on that rotating mandrel. So as the mandrel rotates, the layer by layer deposition of chemical vapor took place, and after desired formation of the preform is obtained, then it is taken out. So this the mixture of the vapors of the starting materials SiCl4, GeCl4, BbR3, etc. is blown through the oxygen hydrogen flame. The soot produced by the oxidation of halide vapor is deposited on cool mandrel. The flame is moved back and forth over the length of the mandrel so that a sufficient number of layers is deposited on it. The concentration of the dopant halide is either varied gradually if index grading is required, or maintained constant if step index fiber is required. So here with the same method we can have both types of fiber fabrication, step index fiber and graded index fiber. If we want to have the graded index fiber, then what is done? The concentration of the dopant halides is changed gradually. So due to gradual change in the concentration, what happens? The refractive index of the material deposited on the mandrel layer by layer keeps on changing gradually in accordance with the requirement, and accordingly the graded index fiber can be obtained. On the other hand, if we want to have the step index fiber, then what is done? The refractive index, the concentration of the dopant is kept constant at desired proportion. Now this is the figure. This figure shows the basic construction or basic schematic diagram of the uh, fabrication technique. So this is the mandrel, and then O2 plus H2 plus halide vapors. Then the vapors are deposited on the rotating mandrel. So porous smooth preform is formed, and then uh, after the deposition of the core and cladding layer is complete, the mandrel is removed. The hollow and porous preform left behind is then sintered in a furnace to form a solid transport glass rod. This is then drawn into fiber. So this is the furnace, and in between the furnace the preform is sintered. With a single preform, 30 to 40 kilometer of fiber can be easily prepared. The index profile can be controlled well using this method, as the flow rate of vapors can be adjusted after deposition of each layer. An attenuation of less than 1 decibel per kilometer of at an operating wavelength of 1.3 millimeter has been reported, but the fiber show an axial dip in the refractive index. So these are some characteristics, or we can say features of the optical fiber prepared or fabricated by this method, OVPO, outside vapor deposition. Now, next method is vapor phase axial deposition. In this method, core and cladding glasses are simultaneously deposited onto the end of the seed rod, which is rotated to maintain azimuthal homogeneity and also pulled up as shown in the figure. So this is the construction or diagram of the uh, vapor phase axial deposition technique. S- s- Now, the porous preform so deposited while the seed rod is being pulled is heated to about 1100 degrees Celsius in an electric furnace in the atmosphere of O2 and thionyl chloride. Any water vapor in the preform is removed through the following reaction. Then the porous preform is then heated to about 1500 degrees Celsius in a carbon furnace where it is sintered into the transparent solid glass rod. A good control over the index profile may be achieved with germania doped coarse graded index fiber with an attenuation level less than zero point 0.5 decibel per kilometer at 1.3 millimeter has been produced by this method. So we will stop here for the time being. Thank you.